All right, get ready to dive into some pretty mind-bending AI stuff today.
Buckle up.
We're talking about AI and reasoning, and, well, imagine you need some serious number crunching for like a big engineering project, right?
Yeah.
You turn to your trusty AI,
Sure.
but every time you run the calculation, it spits out a different answer.
Oh.
Not exactly reassuring, is it?
No, not at all, especially when you're building a bridge or something like that.
Exactly. And that's the kind of problem this paper, are your LLMs capable of stable reasoning? Tackles head on.
It really digs into this often overlooked issue of, how consistent AI reasoning really is.
Okay, reasoning stability for those of us who aren't AI whizzes, break that down a bit.
Well, think of it like, we see all these headlines about AI doing amazing things.
Right. Yeah.
Beating humans at chess, writing poetry, all that.
Superhuman performance, yeah.
But this research is saying, hold on a second, are those results just a fluke? Or can these models really think reliably?
So it's like that friend who's brilliant sometimes, but other times they can't even find their own keys.
Yeah, exactly. High potential, but not exactly someone you'd trust with a complex task every time.
And when we're talking about real-world AI, like self-driving cars or medical diagnosis, that inconsistency is a major red flag.
Absolutely. We need AI that we can depend on that gives us the same correct answer every time.
Okay, so how do we even measure this stability? I mean, aren't those standard AI tests all about getting the right answer, period?
That's part of the problem, actually. The traditional way of measuring AI performance, like greedy accuracy, it just looks at the first answer the AI gives.
So it could get lucky.
Exactly. And even those pass at K metrics, where the model gets a few tries to get it right.
Right, I've heard of those.
They only show us the potential, not the actual consistent performance.
So an AI could score high just by stumbling on the right answer once out of 100 tries.
Precisely. That's where this paper brings in a new metric. G pass at K.
G pass at K.
Yeah. It's basically saying, okay, how consistently can this AI produce the right answer over multiple runs?
So not just hitting the target, but hitting it every time.
Exactly.
Yeah.
And it also introduces this threshold that lets researchers see how the model does under different levels of strictness.
So it's like judging an Olympic athlete, one good performance doesn't make you a champion, right? You need to see that consistency.
Exactly, yeah.
Okay, so G pass at KIOE. I'm starting to see why this is a big deal. But before we get into the results, let's talk about the testing ground, live math bench.
This is where it gets interesting.
Yeah, it sounds like a pretty hardcore challenge for these AIs.
It is, and it was designed that way on purpose. The researchers wanted to avoid this thing called data leakage.
Data leakage, okay.
Which is basically when the AI might have already seen the test questions or something similar during its training.
So it's like acing a test because you peeked at the answers beforehand.
Yeah, exactly. Live Math Bench is constantly evolving with new, tricky problems added all the time to prevent that kind of cheating.
So it's keeping the AIs on their toes, making sure they can really think on the fly.
Precisely. And to make things even tougher, they pull questions from some of the most challenging math competitions out there.
Okay, like what?
The CNMO, the Chinese Math Olympiad. They've got problems from the CCEE, the Chinese college entrance exam, notoriously difficult.
Oh yeah, I've heard horror stories about that one.
And to really push those top-tier AIs, they even included problems from the William Lowell Putnam mathematical competition.
The Putnam exam, that's the stuff of legends, isn't it? I've heard even brilliant math students get stumped by those problems.
It's basically the intellectual Olympics for AI.
So Live Math Bench is like a gauntlet designed to separate the truly insightful AIs from those that just got lucky or memorized a bunch of stuff.
Yeah, it's a real test of their reasoning abilities.
All right, the stage is set. We've got our challenging benchmark, our new evaluation metric. Let's talk results. What happened when they put these latest and greatest LLMs through their paces?
Well, the findings were pretty revealing. And to fully appreciate them, we need to dive into the specific types of models that were evaluated, starting with a family of models called LongCo. Welcome back.
So last time, we left off with this idea of long-co models.
Right.
What makes these models special, and why are they so important in this whole reasoning stability thing?
Well, LongCo stands for long chain of thought.
Okay.
And these models are designed to be really good at breaking down complex problems into smaller steps, like a human would.
So instead of just giving you the answer, they show you how they got there.
Exactly, like a step-by-step solution.
So it's not just about whether the AI gets it right, but how it arrives at that answer.
Exactly, and whether that process is consistent.
Right, because that's what we're really trying to figure out here. Can AI reason reliably, not just get lucky?
Exactly.
So how did these long cope models perform on Live Math Bench? Did all that step-by-step reasoning lead to more stability?
It's kind of a mixed bag.
Okay.
They did do better than other models on those public benchmarks we talked about.
So a point for the idea that more deliberate reasoning leads to better performance.
Seems like it. But here's the thing.
Yeah.
Even the long COP models weren't perfect when it came to stability.
Ah,
When they were tested with GPass at K, especially with a stricter setting, their consistency wasn't always there.
so they could show impressive reasoning sometimes, but they couldn't always replicate it.
Right, which tells us we still haven't figured out how to make AI think consistently, even with these fancy architectures.
It's like we're still scratching the surface of what AI can really do.
We're getting there, but it's a journey.
So it's not just about making bigger models then. We need to understand how reasoning actually works.
Exactly. We need to dig deeper, figure out how to make AI more adaptable and robust, like human intelligence.
Now, you mentioned that there was variation in stability even among these top-performing long-cod models.
Yes, that was interesting, wasn't it?
So it's not just the type of model, but the type of problem as well. Some problems are just harder for AI to reason about consistently.
That's what it looks like, yeah. Remember, Live Math Bench has questions from all sorts of sources.
Yeah, from high school level stuff to those crazy Putnam problems,
Yes.
a real spectrum of difficulty.
And what they found was that models that did great on the easier problems, like the CCE stuff, they often struggled with those harder WLPMC questions.
So it's like acing the quizzes but bombing the final exam.
Yes, exactly like that. Their knowledge might be there, but the deeper understanding to tackle those really tough problems.
Right, that's a really good point, because we can't just assume that an AI that does well in a simple setting will do well in the real world, which is full of messy, complex problems.
Absolutely, it's a whole different ballgame.
This is making me rethink how I look at those headlines about AI outperforming humans. It's not just about winning, it's about consistency and being able to handle the unexpected.
Exactly, and that brings us to another critical point, the issue of data contamination.
Okay. Data contamination, that sounds kind of scary.
It can be. It's basically when the data used to test the AI has leaked into the data used to train it.
So it's like giving a student the answers before the test.
Yeah. They might score well, but it doesn't actually reflect their true understanding.
So how does data contamination mess with the stability of AI reasoning?
Well, they did this experiment where they deliberately contaminated the training data of a model.
Intentionally.
Right.
So they controlled how much the AI could cheat.
Yeah, and as they added more contamination, the model's initial accuracy went up, as you might expect. But here's the thing.
Yeah.
The GPass at K scores, especially with a strict, they didn't improve at all. In fact, sometimes they got worse.
Wait, so the AI was getting more answers right, but its reasoning was becoming less stable? That's kind of weird, right?
It seems counterintuitive, but it shows us that contamination might be hiding the AI's true weaknesses.
Like it's memorizing answers instead of actually understanding the concepts.
Exactly. And this has big implications for how we build and test AI. We need to be really careful about contamination and look beyond those simple metrics that might be hiding a lack of real understanding.
It's like we're pulling back the curtain and seeing how the AI sausage is made.
Yeah.
And it's not always pretty.
Right. And it emphasizes the need for more transparency in AI research.
Absolutely. We need to know what these models are really capable of, not just what they look like on the surface.
Transparency and rigorous evaluation, those are key.
So big picture, what are the main takeaways from all this? What have we learned about reasoning stability in LLMs?
I think the biggest takeaway is that we're still in the early stages of understanding how to build truly intelligent machines.
Even with all the progress we've made.
Exactly. This research is a reality check. It tells us that building bigger models isn't enough.
We need to go deeper, understand how reasoning works, how to make AI adaptable and consistent.
Think about it this way. It's like the difference between training a parrot to repeat phrases and actually teaching it to understand the meaning behind those words.
Ah, that's a good analogy.
We need AI that can reason, not just recite.
And tools like GPass at Kai can help us get there, right?
Absolutely. GPass at K gives us a much better way to measure the consistency of AI reasoning.
It's like we finally have a ruler that actually measures what we want to measure.
Exactly. And when we combine that with benchmarks like Live Math Bench, which really push these models to their limits.
We get a much clearer picture of what AI can really do, where it excels, and where it still struggles.
It's about moving beyond those flashy headlines and digging into the nitty-gritty details.
This whole conversation has been eye-opening. It's made me realize how much more there is to AI than just raw performance numbers.
It's about understanding the nuances, the complexities, the potential pitfalls.
And that brings us to a final thought, something to leave our listeners with.
The research suggests that simply making bigger models might not solve this stability problem.
So what else can we do?
That's the question we need to grapple with as a field. Could it be new training techniques, different architectures, or even a completely different approach to AI development?
It's a challenge that takes us beyond the hype and into the core of what it means to create truly intelligent machines.
It's a journey of exploration and discovery, and it's just getting started.
Well, that's a great note to end on. It's been a fascinating deep dive into the world of AI reasoning.
A real pleasure to be here.
To our listeners, thanks for joining us. We encourage you to check out the research paper we discussed today. You'll find a link in the show notes.
Stay curious, keep exploring.
And until next time, keep those minds engaged.